Welcome back to the Explainer. So when folks argue about Ethereum and Solana, it is almost always about the visible surface level stuff, right? You hear these endless debates about gas fees, transaction speeds, or the developer experience of writing in Solidity versus Rust. But today, we're zooming right past all of that. We're going to put on our security researcher hats and figure out what truly matters when it comes to keeping literally billions of dollars safe. We are exploring how the underlying execution models of these two massive ecosystems fundamentally shape the way smart contract bugs actually manifest.
Okay, let's dive into this. Here's our roadmap for today. First, we'll go beyond the surface to define execution models. Then we look at universal security threats. After that, we'll unpack the EVM as a shared ledger and contrast it with Solana's explicit execution context. Finally, we bring it all together by looking at how auditing actually works in these different execution worlds.
So part 1, beyond the surface.
It's incredibly tempting to just compare spec sheets when looking at these networks, isn't it? But judging Ethereum and Solana purely on technical specs or their programming languages completely misses their hidden depth. So what really separates Ethereum and Solana? I want you to actually think about that for a second. You already know they're both programmable blockchains. You know they both let devs build decentralized apps, lending protocols, and exchanges that run deterministically without a central operator. That's the shared promise. But the real separation isn't about speed. The separation is about the invisible physics of their respective universes.
And those physics? They're defined by the execution model. Basically, this is the set of rules, constraints, and assumptions that dictate how code interacts with state, value, and permissions. This hidden layer is exactly what dictates how vulnerabilities happen. Think of it like a giant puzzle. The rules of a protocol don't just exist in a vacuum. They execute under a specific set of assumptions provided by the environment itself. This environment defines what state even means, how execution is ordered, and what guarantees the system gives you versus what you, the developer, have to manually check yourself.
Which brings us to part 2, universal security threats.
Before we put these two titans head-to-head, we absolutely have to establish their common ground. Because, well, financial logic is financial logic. Whether we're talking about broken accounting, incorrect permission logic, unsafe liquidation rules, or inconsistent share calculations, if a protocol has flawed business logic, it's vulnerable everywhere. If your math for calculating a liquidation threshold is just wrong, it doesn't matter if you wrote it in Solidity, Rust, or jotted it down on a napkin, you are going to get drained. A security researcher always asks first, does this protocol actually do what it mathematically claims to do? Yes, but, and this is a massive but, these mathematical rules are eventually compiled and run by a specific runtime, and that is exactly where the roads diverge.
Let's get into part 3, EVM, the shared ledger. Let's shift our focus to the Ethereum Virtual Machine, framing it through the lens of a shared, continuous history. The entire EVM mindset revolves around a shared ledger. It is all about state transitions. In Ethereum, a contract has its own code, its own storage, its own balance. Every transaction executes in a highly deterministic order, and every single state change becomes a permanent part of this massive, shared global history. On the flip side, the Solana mindset is totally different. It revolves around resource management, authenticating explicit resources inside an isolated execution context. But let's keep our focus on Ethereum for just a minute.
And this brilliantly illustrates why Solidity was created specifically and exclusively for the EVM. It gives developers a powerful, high-level abstraction so they don't have to manually handle every low-level resource or memory layout. Because of this, the EVM feels exactly like a shared ledger with programmable rules. You're essentially just defining how your specific section of the ledger should evolve over time.
So, how does this actually translate into vulnerabilities? Well, if we map the famous EVM bugs we always hear about directly to their root causes in the execution model, a really clear pattern emerges. In the EVM, bugs aren't just isolated spelling mistakes in the code. They're failures of the protocol's internal ledger to remain consistent during those ordered transactions. Take reentrancy, for example. It is fundamentally a state transition failure. Why? Because the contract's internal accounting gets interrupted and fails to update before value is transferred. It breaks the ledger's consistency. Or look at stale Oracle assumptions. That's a failure to preserve the internal book relative to the outside world. On the EVM, the ultimate security question is always this. Does every allowed interaction preserve the protocol's invariance as the ledger actually changes?
Moving on to part 4, Solana and the explicit execution context.
Now we're jumping into the Solana ecosystem. And honestly, we have to completely throw out our EVM mental model. In Solana, programs contain logic, sure, but state lives in completely separate accounts that hold data, permissions, and LAMP ports. which are essentially fractions of Solana tokens. This is pretty wild if you're coming from Ethereum. Your smart contract, or program in Solana terms, doesn't hold user balances inside its own storage. Instead, accounts are passed into the instruction from the outside. Rust fits this incredibly naturally because it's a systems programming language. It is way closer to low-level memory layout and resource management, unlike Solidity, which was explicitly tailored for just one specific virtual machine.
Now, what's really interesting about this is the gauntlet a Solana program has to run through. These are the mandatory hurdles a program must clear before it even touches the core financial logic. Step 1, it receives the explicit accounts. Step 2, it has to verify if the right people actually signed the transaction and if the accounts are allowed to be written to. Step 3, it checks ownership, like, is this account actually owned by the program we think it is? And it validates the program-derived addresses, or PDAs, which are basically specialized accounts controlled by the program itself. Only after all of that defensive checks and balances work is done do we finally hit step 4, actually executing the financial business logic. In Solana, you're essentially a bouncer at a club, checking a dozen IDs before you let anyone near the vault.
Because of those hurdles, we get a totally unique list of vulnerabilities. A massive part of Solana security is simply checking if the execution context is authentic. That's exactly why you see bugs like missing signer checks or account substitution, where an attacker passes in a fake malicious account that looks exactly like a real one. If the program trusts a bad context, it gets exploited. The financial math in step 4 could be absolutely flawless, perfect in every single way, but if the program allowed an attacker to substitute the fee account for their own personal wallet in step 1, boom, it's game over.
Bringing us to our final section, part 5, auditing the execution world. Let's synthesize all of this. This matters deeply to anyone building, investing, or auditing in Web3, because an auditor has to ask completely different questions depending on the assumptions built into the ecosystem's base layer. For the EVM, you are utterly obsessed with order and state transitions. Does the internal accounting remain consistent across ordered transactions? But jump over to Solana, and the auditor's brain has to totally pivot to context authentication. Are the provided accounts authentic, correctly constrained, and connected as intended? You literally cannot take an EVM security checklist and apply it to a Solana program. The physics of the worlds are just too different.
The crucial takeaway here is this: logical bugs are universal, but execution model bugs are shaped by the ecosystem. A decentralized vault or an automated market maker needs sound financial math everywhere, for sure. But the environment, whether that's the shared ledger of the EVM or the explicit resource management of Solana, completely dictates the unique technical threats. Mismatches between what a developer assumes the environment is doing and what the environment actually guarantees, well, that's exactly where the most devastating hacks occur.
Which leaves us with this final, vital question to ponder. When you're looking at a smart contract, are you just reading code, or are you actually understanding the world in which it executes? Because as we've seen today, the rules of the world dictate the reality of the code. Thank you so much for joining me on this deep dive into blockchain execution models. Keep exploring, keep learning, and we'll see you in the next explainer.